In this lesson, we'll look at probabilities of multiple events. We'll talk about two different types of events. One where the probability of the second event is not affected by the probability of the first event. So those are called independent events if one does not affect the other. And if the first event does affect the probability of the second, this is called dependent events. Let's take a look at a few examples of these. If I choose a card from a deck of cards, and for instance, I choose the Ace of Spades, I replace it, and then I shuffle the cards, and then I choose a card again from the same deck of cards. Those are independent events because the outcome of the first pick does not affect the outcome of the second pick because I've replaced the card and shuffled. However, our second scenario is choosing a card. So for instance, if I choose the Ace of Spades, for instance, and I don't replace it, then the second time I draw this, the probability that I'm going to draw the Ace of Spades is actually 0, and the probability that I'm going to draw any other card is 1 over 51 rather than 1 over 52. So those guys are dependent events. If I roll a pair of dice and then I roll the same pair again, the probabilities are the same each time, so they're not affected by the other roll. So those would be independent events. And then if I pick a marble from a bag of 10 marbles and 10 white marbles without replacing it and then pick a second marble, the probability of the second pick is affected by what happened on the first pick. So those are dependent events. If I choose a shirt to wear and then I check the weather report in New York, those are totally unrelated events. So they are going to be independent of each other. However, if I check the local weather report and then I decide what to wear to school, those are likely dependent events because I may choose something that's weather appropriate. All right, if I have two independent events, then the probability of A followed by B is equal to the probability of the first one times the probability of the second event. We can illustrate this with a tree diagram. So at a picnic, there are 10 diet drinks and 5 regular drinks. There are also 9 bags of fat-free chips and 12 bags of regular chips. So my probability of grabbing a diet drink is, without looking, would be 10 out of the 15 total possible drinks, so that's going to be a probability of 2/3. My probability of grabbing a regular drink without looking is 5 over the total 15, because there are 5 regular drinks, and that reduces to a probability of 1/3. As far as grabbing fat-free chips, there are 9 bags of those out of the 21 total, so that's going to reduce to 3/7. And then grabbing a bag of regular chips, there are 12 of those out of the 21 total, and so that reduces to 4/7. So the probability of grabbing my diet drink is 2/3 and a regular drink 1/3. The tree diagram will help us sort of organize the probabilities. And then the probability that after that I grab my fat-free chips is 3/7. And probability of grabbing my regular chips are 4/7. And those same probability exists if I grab the regular drink the first time. Now the probability of grabbing a diet drink and fat-free chips is 2/3 times 3/7, which would give us 6/21, and that's going to reduce to 2/7. And then my probability of grabbing a diet drink and regular chips would be 2/3 times 4/7. I can just use the two probabilities on the tree diagram, and that gives us a probability of those two happening together of 8/21. Probability of grabbing a regular drink and fat-free chips is 1/3 times 3/7. That will give us 3/21, which reduces to 1/7. And the probability of grabbing both regular drink and regular chips is 1/3 times 4/7, or 4/21. I want you to notice something about all four of those probabilities. If you add them up, looking at the 21st, 6 21st plus 8 21st is 14 21st, plus 3 21st is 17 21st, plus 4 21st is 21 21st, or 1 or 100%. What's the most likely event to happen? Looks like grabbing a diet drink and regular chips has the highest probability of happening. All right, another vocabulary word for you. Events that cannot occur at the same time are called mutually exclusive. So that just means that one event excludes the possibility of the other event happening. If two events are mutually exclusive, the probability of them both happening is 0, or the probability of A and B is equal to 0. So let's take a look at a couple of events here. In example 2, you roll a single die one time. So we are going to determine if these are mutually exclusive and then find the probability of both outcomes. Probability of rolling a 2 versus rolling a 3. Is it possible to get a 2 and a 3 on my single roll? No, those are mutually exclusive. So that means the probability that both of those things are going to happen on a single roll is equal to 0. Okay, how about even number and rolling a multiple of 3? Well, those guys do have some crossover. They're on a die, there is. Our next pair of events, rolling an even number and rolling a multiple of 3, are not mutually exclusive. And that is because an even number that is also a multiple of 3 on a die is 6. So the probability of A and B happening together is the product of their probabilities. The probability of rolling an even number is 3 out of 6, because there are 3 even numbers on a die, times the probability of rolling a multiple of 3, which would be 2 multiples of 3 out of 6. So that's going to give us 6 36ths, or 1/6. All right, now we're going to take a look at the probability of A or B. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B happening together. In other words, we're going to add their probabilities, but then we're going to subtract out the probability that happened together, because that will have been counted twice. Now, if you have mutually exclusive events, the probability that they're going to happen together is equal to 0. So therefore, probability of mutually exclusive events is just the sum of the two probabilities. At Panther High, a student can take only one foreign language each term. About 37% of students take Spanish and 15% of students take French. Are these mutually exclusive? The answer is yes. And that's because they're not allowed to take more than one language. So if they are mutually exclusive, what is the probability that a student takes either Spanish or French? That would just be adding their two probabilities, which would be 37% plus 15%. I'm just going to give my answer as a decimal. So that will be about 52% probability. All right, let's take a look at the next situation. We're picking from this dish and selecting a token at random. What is the probability that the token is either round or green? So let's count up our round tokens first. There are 1, 2, 3, 4, 5 round tokens. So 5 out of the 9 are round, plus the probability of our greens. There are 3 green tokens, so that's 3 out of 9. And now we have to subtract out the ones that we've counted twice. So the ones that we counted twice are the ones that are both round and green, and there are 2 of those. So 5 plus 3 minus 2 is equal to 6/9, or in lowest terms, 2/3. Let's skip B. Let's take a look at the third one. What is the probability that we select either a green or a square? So we've said before there are 3 out of 9 green tokens. And let's count up our squares. It looks like we have 3 squares in there. So the probability of picking a square is 3 out of 9. Now we have to subtract off, since we've counted them twice, the green squares. Well, there's only one of those, so our total probability here is 5 out of 9. Next, we're going to take a look at something called conditional probabilities. Sometimes conditions change the probability that event occurs. So the probability that event B will occur given that A has already occurred is what we call a conditional probability. And the notation that for the probability that B will occur given that A has already occurred is this right here. It looks like a fraction almost. Probability that B happens given that A occurs. All right, let's take a look at an example of this. This table shows the number of students sorted by gender in 2-year, 4-year, and graduate schools during 2005. If you pick a student randomly from this group, we want to use the table to find each probability. So the probability that you pick a female, given that you already know that this student is a graduate school student. So we're going to be just looking at our graduate schools because we're assuming that we know already that this person is a graduate school student. So just looking at our graduate students, we have 1,954 females out of 3,303 total graduate students. And now we can take and get a decimal approximation for that. So 1954 divided by 3,303, and Control Enter if you want to change that to a decimal. We are going to give our answers as decimals here, and we'll round to the nearest hundredth, which is equivalent to rounding to the nearest percent, so about 59%. All right, now let's take a look at the probability that a student is female, given no constraints. So the probability that a student is female would just be the number of total female students, 9,933, out of the total number of students, 17,472. Let's take that one and convert that to a decimal as well. 9,933 divided by 17,472. And that gives us about 0.57 or 57%. So we can see that these are not independent of one another, right? The fact that a student is a graduate school student makes it more likely that they are female. All right, let's check out the next one, probability of a 4-year college student. So we're just looking at our 4-year college students out of our total number of students. So 4-year college students out of the total number of students would be 9,841 divided by 17,472. And so let's take and convert that to a decimal. 9,841 divided by 17,472. And that gives us about 56%. And then we have a conditional probability next. Probability that a student is a 4-year student, given that we already know that the student is male. So now what we're going to do with our chart is we're going to only draw our attention to the male students, so there's this column. So what is the probability that out of those students that a student is a 4-year college student? So that would be 4,324 out of our total male students, 7,539. Let's convert that to a decimal. 24 divided by 7539, Control Enter for a decimal, is about 57%. So we can see that if for male students, it's a little bit more likely that they are a four-year college student. All right, let's take a look at this waste collection example. This is data from 2007. What is the probability that a sample of recycled waste is metal? So we're looking for the probability that something is metal given that we already know that it was recycled. So we're going to be just looking at our recycleds, and the probability that it is metal is 7.2 tons out of 79.4 tons. Let's convert that to a decimal as well. And that gives us about 0.09 or 9%. All right, and that brings us to formalizing this a little bit more. If we have not actual data in terms of totals, we're going to convert our condition. We're going to compute our conditional probability using the following formula. The probability of A given B is equal to the probability of A and B happening together over the probability of B. So we'll use this Venn diagram that shows probabilities for events A and B. What you should know is that the orange portion of this shows when event A is happening alone. The green portion is where event B is happening alone. Where those two overlap is where events A and B happen at the same time. So that occurs 5% of the time. All right, probability of A is just our 15% plus 5% areas, which will give us our 20%. We'll just leave that as a decimal. And then the probability of B, that would be that circle where we have B, which is a total of 25%. So B occurs 25% of the time. The probability that either A or B happens would be the probability that A happens plus the probability of B happens minus their overlap, because now we counted it twice. So that would be a total of 40%. Probability that A and B happen together is that overlap, that's 5%. The probability that neither A nor B happens is everything in that yellow area outside of the circles for A and B. Well, we saw in C that the circles A and B comprise 40% of the time, so the probability that neither one of them happens would be 100% or 1 minus 40% or 0.4. That's going to give us 60% for the probability that neither one of them happens. Now we have some conditional probabilities to compute. The probability that A happens given that B already happens is the probability of A and B happening together, that's our 5%, divided by the probability that B happens, which is our 25%. That's 5 out of 25, which is 1/5, and our 1/5 converts to a decimal, 0.2. You can either do that on your calculator or in your head. Probability that B happens given that A happens is the probability that they occur together, divided by the probability of A, which is 0.20. And so that's 5% out of 20%, which is 1/4, and that's 0.25. Now what you might notice here is that the probability that A occurs is 20%, and the probability that A occurs given when that B has already occurred is also 20%. That means that B did not have any effect on A's probability of occurring. The same thing happens with B and A. Probability that B occurs regardless of whether A has occurred is still 25%. So it appears that events A and B are independent. So I'm going to answer yes. And how do I know? I know because the probability that A occurs is equal to the probability that A given B occurs, and the probability of B happening is the same as the probability of B happening given A has already happened. All right, we're going to do one more here with a tree diagram. So a jar contains 5 marbles, 3 black and 2 white. 2 marbles are drawn without replacement, and we're going to use the tree diagram before we answer each question. So we have 2 outcomes possible. When we draw the first marble, it can come out black or white. When we draw the second marble, it can either come out black or white as well. Now the first time that I draw, we have 5 marbles total, 3 are black. So that means we have a 3/5 chance of drawing a black marble, 2/5 chance of drawing a white marble. Once we've already drawn the black marble, then there are only 2 black and 2 white left, so drawing another black marble has a 2/4 or 1/2 chance, and drawing another white marble has a 1/2 chance as well. If we draw a white marble the first time, then there are 3 black and 1 white left, so our probability of drawing a black marble is now 3/4, and the probability that drawing a white marble is 1/4. So, probability of black and black is 3/5 times 1/2 is 3/10. Probability of black and white is 3/5 times 1/2 or 3/10. Probability of white and black is 2/5 times 3/4, and that's going to give us 6/20, which reduces to 3/10. And lastly, the probability that we draw a white and then another white is 2/5 times 1/4, which will give us 2/20 or 1/10. So, looking at all of these individual probabilities, what's the probability that both marbles are black? Well, that would be our top probability, black followed by black. That would be 3/10. What is the probability that exactly 1 marble is black? Exactly 1 marble is black in both of these scenarios, right? So that's actually 6/10 of the time. And what is the probability that at least 1 marble is black? So that would be probability that we get black and black, or black and white, or white and black. So add all 3 of those probabilities together and we get 9/10. That will be it for the lesson.